What if the ordered beauty we see in everyday crystals, like a simple grain of salt, or even the intricate six-fold geometry of a snowflake, is just a fleeting glimpse of a far grander, hidden architecture that structures all of reality?
Hmm.
And what if the universe isn't simply three-dimensional, but patterned in profound ways that govern everything, from the smallest subatomic particles to the largest cosmic structures we observe?
It's a truly thought-provoking idea, isn't it? We often perceive our world as solid and predictable, built on familiar dimensions.
Right.
But what if that very predictability, that underlying order, stems from something far more complex, operating in dimensions beyond our immediate grasp?
Exactly. And today, we are diving deep into an extraordinary theoretical concept that promises to challenge our very understanding of matter, space, and even the nature of intelligence itself. Hypercrystals.
Uh-huh.
You are about to embark on a journey that, frankly, could redefine the fundamental fabric of everything you thought you knew about reality.
This deep dive is grounded in a groundbreaking theoretical framework from a recent paper titled Hypercrystals and Hypercrystallization, authored by Philip Randolph Lillian and published just this year in 2024.
Very recent.
Very. And this isn't just a simple hypothesis. It introduces something truly ambitious, something the author calls the hypersymmetric, hyperdimensional, hyperspace coherent resonance theory of everything. Or, well, for simplicity, we'll refer to it as the HHHCR-TOE.
HHHCR2.
Got it.
Our mission today is to unpack this incredibly dense yet utterly fascinating material. We're going to extract the most insightful nuggets, clarify some truly mind-expanding concepts, and explore how this theory proposes to redefine the very fabric of our reality.
Yeah, it's ambitious stuff.
We're talking about everything from the fundamental nature of space and time to the origin of intelligence and even the potential for entirely new energy sources. Get ready for some serious revelations, because this theory suggests the universe is far more coherent and interconnected than we ever imagined. Okay, let's begin by grounding ourselves in the familiar. When we talk about crystals, what does that traditionally mean? Most of us picture something like the clear facets of quartz or the crystalline structure of table salt.
Precisely. At its most basic, a traditional crystal is a material where its constituent atoms or molecules are arranged into a highly ordered periodic structure.
Like a grid.
Exactly, like a perfect repeating 3D grid. Think of it like a perfectly repeating pattern in 3 divisions. The key property here is what we call translational symmetry. Meaning, if you move a certain distance in any direction within the crystal, you'll find the exact same atomic arrangement repeating itself perfectly, like an infinitely extending 3-dimensional wallpaper pattern. This predictable repeating unit cell is fundamental to their properties.
Okay, simple enough. But science, as it always does, loves to challenge established paradigms. And that leads us to a fascinating stepping stone, a truly significant scientific breakthrough: the Quasicrystal Revolution. This discovery dramatically challenged that traditional understanding of crystals you just described.
It was a monumental shift in our understanding, really. For over 150 years, crystallography was based on the premise that only certain rotational symmetries were allowed in periodic crystals, specifically 2-fold, 3-fold, 4-fold, and 6-fold symmetries.
Right, those are the rules.
5-fold symmetry was explicitly forbidden because you couldn't tile a 3D space with a repeating unit that had it. It just didn't work geometrically.
Until it did.
Until it did. Then, in the 1980s, the discovery of quasicrystals shattered that assumption. Unlike traditional crystals, which strictly adhere to that repeating periodic arrangement, quasicrystals exhibit long-range order, but without strict periodicity.
Ordered, but not repeating. How does that work?
Imagine a pattern that looks highly organized and intricate, but it never quite repeats itself in the exact same way. They can display non-crystallographic rotational symmetries, most famously 5-fold symmetry, which was supposed to be impossible.
That's truly incredible, ordered, yet non-repeating in the way we understood crystals to be.
Yeah.
But here's where it really starts to twist our perception. The paper introduces the concept that quasicrystals can be mathematically understood as projections of periodic structures from a higher dimensional space.
Mm-hmm.
Can you explain that perhaps with an analogy? It sounds tricky.
Certainly. Think of it this way. Imagine you have a perfectly periodic repeating grid, not in our familiar 3 dimensions, but in, say, 5 dimensions, a 5D lattice.
Okay, hard to picture, but okay.
Now imagine shining a light through that invisible 5D lattice and casting its shadow or projection into our familiar 3D space. That shadow could form a complex structure like an icosahedral quasicrystal, which has that forbidden 5-fold symmetry.
Ah, so the weirdness in 3D comes from a regular pattern in 5D.
Exactly. The 5D lattice itself is perfectly periodic, but when you reduce its dimensionality through projection, the resulting 3D object appears to have long-range order, but without the strict, simple periodicity we expect in our world. It's a way of saying that the complex, almost paradoxical 3D structure we see is actually a simplified manifestation of a more ordered, periodic structure in a higher dimension.
Wow.
And this sets a crucial precedent for us, hinting that the universe might operate on principles that extend beyond our immediate spatial perception.
And these quasicrystals aren't just theoretical curiosities, right? They've found significant real-world applications.
Indeed. Despite their complex nature, quasicrystals have already found practical uses due to their unique properties. Their high strength, low friction, and exceptional hardness make them ideal for aerospace components.
Like what, specifically?
Things like coatings for engine turbine blades or bearings, where extreme durability and reduced wear are critical. They just hold up incredibly well.
And you mentioned medical uses, too.
Yep. Yes. They also exhibit remarkable biocompatibility and corrosion resistance, making them excellent candidates for advanced medical implants.
Like joint replacements, I imagine, where durability and safety are paramount. That low friction must be key there.
Exactly. For medical implants, quasicrystalline coatings provide superior biocompatibility, meaning they integrate well with biological tissues, and corrosion resistance, which is vital for long-term use within the body. And yes, their low friction significantly reduces wear and tear on the implant itself and surrounding tissues. That's crucial for the longevity and success of devices like hip or knee replacements.
Makes sense.
The paper even delves into detailed optimization methods for these medical applications. For example, surface treatments like etching or sandblasting are used to create micro and nanoscale roughness on the coating.
Why rough? Wouldn't smooth be better for friction?
But this roughness enhances cell adhesion and promotes osseointegration, where the bone actually grows onto and integrates with the implant. It makes it much more stable.
I see. So it's a trade-off, or rather, optimizing different properties.
Right. And then techniques like direct metal laser sintering or DMLS are employed to create incredibly smooth, defect-free coatings in other areas or overall structures that do minimize wear and improve patient outcomes. It's a remarkable fusion of advanced physics and practical engineering.
That's incredibly impressive for a material that initially broke all the old rules of crystallography. Which brings us to the next logical, albeit much bigger, leap into hypercrystals.
The main event.
So if quasicrystals are projections from higher dimensions, what exactly are hypercrystals? How do we define something that's, well, hyper in this context?
Hypercrystals are a profound theoretical extension of ordinary crystals, but into dimensions beyond our familiar 3. Their lattice structures are simply not confined to our 3D space. They are truly existing and organized within these higher dimensions.
So patterns in 4D, 5D, or more.
Exactly. Imagine those repeating patterns, but now they repeat, or maybe quasi-repeat, across 4, 5, or even more spatial dimensions. They represent an entirely new class of ordered matter.
So a supercrystal existing in a superspace. What new properties or symmetries do they possess if they're not limited by our 3D rules? What makes them so special?
Well, they exhibit entirely new, far more complex symmetries or quasi-periodic arrangements that reflect an underlying hypersymmetry. These symmetries are beyond what we can visualize directly in 3D, but they are mathematically precise and govern the organization of these structures in higher dimensions.
Okay, more complex rules.
But what makes them so intriguing, and this is truly a crucial insight for you, the listener, is that the paper directly associates hypercrystals with regions of enhanced quantum coherence.
Quantum coherence. Okay, let's unpack that.
Right.
For those who might not know, it's vital for cutting-edge technologies like quantum computing and quantum teleportation, right?
Absolutely.
It's about maintaining the delicate, synchronized state of quantum information, allowing particles to exist in multiple states simultaneously or to be linked across vast distances. But maintaining that coherence is incredibly difficult in our noisy 3D world, right? Qubits are notoriously fragile.
You're absolutely right. Decoherence is the single biggest hurdle in quantum computing. Qubits, which are the fundamental units of quantum information, are incredibly susceptible to environmental noise, thermal fluctuations, unwanted interactions. You name it.
They lose their quantumness easily.
Exactly. Even the slightest disturbance can cause them to lose their quantum state, their superposition or entanglement, and collapse into a classical state, destroying the quantum information. This is why quantum computers typically require extreme cooling, like near absolute zero or elaborate isolation systems.
And this is where hypercrystals come in. They offer a fundamental solution.
That's the proposal. Hypercrystals, by their very nature as stable, highly ordered, and coherent regions within this larger hypersymmetric hyperspace, could fundamentally protect quantum information.
How?
The theory suggests that their multidimensional structural integrity, inherent stability, and coherent resonance within hyperspace create a kind of natural fault-tolerant bubble. Within this bubble, qubits are intrinsically isolated from the decohering effects of our ordinary 3D environment.
Like a higher dimensional safe room for quantum states.
Sort of, yeah. Imagine a perfectly structured vault that inherently protects its contents not just by its walls, but by its very design being in a higher, more stable dimension. This makes them theoretical, fault-tolerant quantum information processing units, a kind of natural, ultra-stable quantum memory.
Because the noise is mostly in our 3D space, and these things exist partly outside it.
That's the idea. Their existence in higher dimensions inherently imbues them with a robustness against local 3D perturbations. The structure itself maintains coherence.
That's a huge leap, linking abstract higher dimensional structures directly to a fundamental solution for quantum technology. But to understand how that works, we need to dive into the foundational concepts of the HHHCR-TOA. Let's start with hyperspace itself, which is described as our universe's hidden dimensions.
Right, the stage.
How do we even begin to conceive of coordinates and geometry in such a space? It's not just XYZ anymore.
Well, the theory introduces the idea of a hypersymmetric hyperspace manifold, which is denoted as Mn, where n represents the number of dimensions. This manifold is effectively the stage upon which hypercrystals exist, extending far beyond our familiar XYZ coordinates.
An n-dimensional space.
And to describe distances and paths within this complex hyperspace, the theory employs Finsler geometry.
Finsler geometry. Okay, that sounds a bit complex. What's special about it compared to the standard Euclidean or even Riemannian geometry we're more familiar with in physics, like in general relativity?
The key difference is that in Finsler geometry, the way you measure distances and paths, the metric, depends not just on your position, but also on the direction you're moving.
Direction matters. How so?
In classical Riemannian geometry, the metric is fixed at each point, regardless of direction. Like, the distance between 2 points is the same no matter which way you face. But in Finsler geometry, it's flexible.
Okay, give me an analogy.
Think of it like this. Imagine a city where the travel time or effort between 2 points changes drastically depending on which direction you leave a specific intersection. If you head north, it's a smooth highway. If you head east, it's a congested, bumpy street. The distance effectively changes based on your direction of travel from that point.
Ah, I see. So space itself isn't uniform.
Exactly. This flexibility is crucial for describing the complex and potentially direction-dependent nature of hyperspace. It implies that space itself isn't uniformly isotropic. Its properties and how energy or information propagates could vary depending on the trajectory within these higher dimensions. Maybe that explains why different forces behave differently or why particles have certain properties.
So it's not a uniform space where every direction is the same. That makes more sense for something hyper. And does this apply to concepts like curvature, which we associate with gravity and the fabric of spacetime?
Absolutely. Even concepts like a black hole's warped spacetime, described by the Schwarzschild metric in our 3D plus time universe, can be generalized within this Finsler framework. Hyperspace itself could be profoundly curved, and this curvature would directly influence the formation, stability, and dynamics of these higher dimensional structures, including hypercrystals. It's a much richer and more dynamic geometric landscape than our familiar flat or simply curved 3D space.
Okay, a richer, direction-dependent, potentially curved hyperspace. Now let's move from the space itself to the underlying rules that govern order within it. How do hypersymmetry and hyperlattices define this higher order? We have symmetry groups in 3D crystallography, but what about hypersymmetry groups?
Right. So in traditional crystallography, symmetry groups like SO3 describe the specific 3D rotations, reflections, and inversions that leave a crystal invariant the operations you can do where it still looks the same. In hyperspace, we're talking about hypersymmetry groups, denoted as H, which are subgroups of SON, where n is greater than 3. These are much more complex groups governing the rotational and translational symmetries within these higher dimensions.
So more ways for something to be symmetric.
Essentially, yes. More complex ways. These powerful groups are absolutely fundamental to defining the specific structures, properties, and even the vibrational modes of hypercrystals. They are the DNA that dictates how order emerges in hyperspace.
And just like quasicrystals showed us, can these hyperlattices also exhibit a periodic order? Structures that are ordered but don't strictly repeat.
That's entirely possible, and indeed a key part of the theory. Even in hyperspace, structures can maintain long-range order without strict periodicity. You can think of them as generalized aperiodic tilings.
Like Penrose tiles, but in more dimensions.
Exactly. Imagine taking a 2D Penrose tiling, which is famously non-repeating but perfectly ordered, and extending the intricate fractal-like concept into higher dimensions. The underlying hypersymmetry allows for this complex, yet highly organized, non-repeating order to exist across multiple dimensions, creating patterns that are locally irregular but globally coherent.
So we're talking about hyperlattice structures that are generalized concepts of periodic arrangements, but now extending into these higher dimensions, defined by lattice vectors spanning this n-dimensional space. But the theory also suggests they have a self-similar organization. What exactly does that mean in this hypercontext?
It means they exhibit a recursive or self-similar organization where patterns repeat across multiple scales within hyperspace.
Like a fractal.
Very much like a fractal. Imagine zooming into a hypercrystal, and as you go deeper and deeper, you keep seeing similar patterns, maybe smaller, maybe rotated, but fundamentally similar structures. This self-similarity isn't just a visual quirk, it's suggested to be a fundamental characteristic that allows for incredible complexity and information storage within these structures, almost like nested structures within structures, extending infinitely across scales.
Fascinating. So we have the space, the rules for arrangement, and now we need to understand the glue that holds these hypercrystals together and dictates their very existence. The theory talks about coherent resonance as the tuning fork of hyperspace. What's the fundamental principle at play here?
Coherent resonance is absolutely central. It's not just a minor detail, it's fundamental to how hypercrystals form, maintain their stability, and interact. The theory introduces a key concept. Resonance functions, denoted as psi of position and time, Eric.
Okay, psi, like in quantum mechanics.
Similar notation, but here it's a scalar or vector field representing the amplitude and phase of coherent resonant waves propagating across hyperspace. It's analogous to how waves behave in our familiar space like electromagnetic waves or sound waves, but extended to higher dimensions. These aren't just abstract math, they're conceptual representations of the fundamental vibrational patterns of hyperspace itself.
Like ripples on a pond, but in a multidimensional pond, where those ripples are the very fabric of reality.
That's a good way to think about it. And within that pond, there are specific locations called resonant points. These are locations in hyperspace where the resonance function's gradient vanishes.
Gradient vanishes, meaning it's flat. A minimum or maximum.
Exactly. For AS0, it means the slope of the resonance field is 0. At these points, the waves constructively interfere, reinforcing each other perfectly to create stable nodes. These nodes are precisely the definition of the hypercrystal structure.
So the hypercrystal is the pattern of constructive interference.
Precisely. Imagine many waves coming together perfectly, their peaks aligning, to form a perpetually reinforced, stable peak ripple in a pond. The vanishing gradient means it's a point of equilibrium, a stable minimum in the energy landscape, making it a natural attractor for the formation of coherent structures.
So it's a dynamic balance. And where does the energy for these stable resonant structures come from? Is it drawn from somewhere or just there?
The total energy of these resonant structures is a delicate and dynamic balance between kinetic energy, which is related to the time, evolution, or motion of the resonance waves themselves, and potential energy, related to the spatial configuration of the waves and their interaction with the hyperlattice.
Wow.
The crucial insight is that this energy isn't simply external. It's sourced directly from the interaction of waves propagating through hyperspace. These could be various forms of energy waves, electromagnetic, mechanical, perhaps even fundamental quantum waves. The hypercrystal stability doesn't come from an external input, but arises from this inherent balance and constructive interference within the system itself, continually drawing energy from the hyperspace environment to maintain its coherent structure.
Wow, okay. So it's self-sustaining through resonance. This all sounds incredibly complex, but also beautifully interconnected. Let's dig deeper into the idea of patterns within patterns, hyperfractal structures. We're familiar with fractals like the Mandelbrot set in 2D, but what does fractal dimensionality mean in hyperspace and what's its significance?
Right, so we're extending the concept of fractal dimensions, usually denoted as df. These are often non-integer dimensions that describe how complex structures fill space at different scales. Think of a coastline. It's more complex than a simple line, 1D, but doesn't fill a plane, 2D.
It has a fractional dimension.
Exactly. In hyperspace, df measures the complexity of the hyperlattice as it scales. So a hyperfractal lattice is a structure that is self-similar, meaning it repeats its fundamental patterns across multiple scales within a hyperspace, and its complexity is characterized by its fractal dimension. It's about how densely and intricately these structures are organized across varying magnifications in higher dimensions.
So like endlessly zooming into a complex mathematical pattern and always seeing similar structures. But now this applies to the very fabric of reality in multiple dimensions.
Precisely. And these hyperfractal lattices are conceptually constructed by recursively applying self-similar transformations like scaling, rotation, or reflection to a base lattice structure.
Can you give an example, like a higher dimensional version of something familiar?
Well, think about higher dimensional generalizations of classic fractals, like the Sierpinski gasket, which is a 2D fractal formed by repeatedly removing triangles from a larger triangle,
Sure.
or the Menger sponge, a 3D fractal formed by repeatedly removing cubes from a larger cube. The theory extends their self-similar iterative nature into 4D or more, creating incredibly rich and information-dense structures woven into the fabric of hyperspace.
Okay, that's truly astonishing. But here's where it gets truly profound for a theory of everything. The theory suggests that the values of fundamental constants in our universe, things like Planck's constant h, which governs quantum mechanics, or the fine structure constant alpha, which dictates the strength of electromagnetic interactions, are not arbitrary.
Right, not just random numbers.
They emerge from the coherent resonance conditions that exist at different fractal scales of hyperspace.
What? This is a bold and ambitious claim, absolutely. It implies that these constants are not simply fixed values chosen at the Big Bang, but rather they are stable resonant frequencies or attractors that naturally emerge from the geometry and dynamics of the underlying hyperfractal continuum.
So the universe naturally tunes itself.
Kind of, yes. Imagine hyperspace as a vast, multi-layered resonant chamber. Different fractal scales within this chamber would support different coherent resonance patterns, like different notes on a musical instrument. The physical constants we observe in our 3D reality are the manifestations of these stable, recurring resonant conditions at specific, fundamental fractal scales.
You mean an example?
For instance, the speed of light might be related to a resonant frequency of information propagation at one universal scale, while Planck's constant is intrinsically linked to the quantum fluctuations and their coherent resonance at a much smaller quantum fractal scale. It means the universe isn't just governed by these constants in a very real sense, it generates them through its own inherent resonant structure. They're emergent properties of the hyperfractal geometry.
Wow, so the very constants that define our reality are a product of this multidimensional fractal resonant soup. That's a truly grand unification. Let's talk about how this theory envisions the shaping of the universe through phase transitions, like water freezing, but cosmic.
Exactly like that, but on a much grander scale. In the HHHCR framework, phase transitions in hypercrystals occur when the system shifts from one state to another, often accompanied by a dramatic change in symmetry.
How is that modeled?
Mathematically, it's often modeled using something called a free energy functional and an order parameter, which we can again call psi, that describes the degree of crystallization. The order parameter essentially quantifies how much the system has transitioned from a disordered state to a more ordered hypercrystalline state. It goes from 0, say, to some non-zero value.
So it's like measuring how icy the water has become, but for the universe's structure.
A good analogy. The emergence of a hypercrystal can correspond to a symmetry-breaking transition. This is where a high-symmetry disordered state like the very early, hot, uniform universe moves to a lower symmetry, highly ordered hypercrystal state as it cools or evolves.
And why is symmetry breaking important?
Because it's essential for complexity. It's analogous to how, in the early universe, fundamental forces like the strong, weak, and electromagnetic forces are thought to have frozen out or become distinct from a single unified force as the universe cooled, or how particles acquired mass after the Higgs field transition. These symmetry-breaking events are absolutely essential for the universe to develop the distinct, complex structures and differentiated particles we observe today, leading to stars, galaxies, and ultimately life. Without breaking symmetry, everything would stay uniform and boring.
Okay, so phase transitions create structure. And it's not just about physical structures. One of the most radical shifts the HHHCR proposes is that information isn't just something we process or measure, it's a fundamental building block of reality itself.
Yes.
It states that hypercrystals aren't just physical structures, they are fundamentally information structures.
This is indeed a core tenet and a deeply philosophical one. The theory posits an information density function that is maximized at the locations of hypercrystals. These are points where order and coherent information are concentrated.
So information clumps together where hypercrystals form.
Kind of. The crystallization process itself involves a transition from a high-entropy disordered state, a state of low information, to a low-entropy, highly coherent state, a state of high information. This increase in order, this reduction of entropy, is measured by negentropy.
Negentropy. Negative entropy. Order.
Exactly. Negentropy, n equals max s, quantifies how much a system deviates from complete disorder. Maximum entropy, SMAX. So a hypercrystal, by its very nature, acts as a local generator and concentrator of negentropy and information. It actively imposes order.
So the more organized a hypercrystal is, the more information it contains, and the lower its entropy. It actively combats disorder.
Precisely. And at the largest scales, hypercrystals are envisioned as fundamental nodes in a vast information network that spans the entire universe.
The cosmic internet.
Yeah, maybe. But this isn't a passive network, it's dynamically active. This network is responsible for maintaining the coherence of the universe, ensuring that physical laws and constants remain consistent across different regions of space, and propagating fundamental information throughout the cosmos. It's like the universe's underlying operating system, constantly working to maintain consistency and order.
That has profound philosophical implications. It aligns directly with the philosophical concept of informational realism. The idea that information is the most basic substance of reality.
That's us.
In this view, everything we observe, from subatomic particles to vast galaxies, can be seen as intricate, dynamic manifestations of these underlying information patterns.
It suggests that information isn't merely a descriptor of the universe, but rather it creates and shapes the universe in an ongoing dynamic interplay. Our physical reality, in this view, is the emergent behavior of a colossal, self-organizing information system. Information comes first.
Which naturally leads us to how this theory reconceptualizes space and time themselves. This is where it gets truly mind-expanding. Let's start with space. It's not just an empty, passive container.
Not at all. The HHHCR proposes that space is not just an empty void or a passive backdrop against which events unfold. Instead, it's described as an active, structured entity.
Active how?
It has inherent properties that exist and repeat at multiple scales due to its hyperfractal geometry. This means space itself becomes a self-organizing system, not merely holding matter, but actively influencing and guiding the formation of matter, energy, and even life within it.
So space has a kind of agency. It's not just where things happen, but it's part of how things happen. It's a massive aha moment for many.
Yeah.
The idea of space as a lifelike system.
Yes, it truly challenges conventional thinking. It implies that space exhibits negentropic behavior. It actively works to maintain and increase order, much like living systems regulate themselves and grow in complexity. It's no longer a static void, but a multi-layered active fabric that's fundamental to the universe's evolution and structure, intrinsically working towards greater coherence and organization.
Wow. Okay. And what about time? For most of us, time is just a linear flow, one moment after another, moving irrevocably forward. But this theory suggests time is also a dynamic fractal dimension.
Time in this framework is indeed not a simple one-dimensional continuum. It behaves like a fractal.
A fractal in time, what does that even mean?
It means it is potentially self-similar and recursive. Temporal structures might repeat at different scales, much like spatial fractals. This fractal nature suggests that traditional linear cause and effect relationships might not always hold in the strictest sense.
Whoa, nonlinear causality.
Potentially. Events could resonate across different scales, meaning a past event might have a nonlinear reverberating echo in the present, or future states could subtly influence past configurations through these higher dimensional temporal connections. It could create unexpected feedback loops that influence the flow of time.
That's a huge departure from classical physics, even from our everyday experience. So time itself can also exhibit coherent resonance, like space.
Absolutely. The theory posits that time itself can exhibit coherent resonance, where different moments or temporal scales align and synchronize. This synchronization might help stabilize the universe's evolution, preventing it from spiraling into complete chaos or stagnation.
So some moments are more resonant than others.
Perhaps. It challenges the traditional view that all moments are equally significant, suggesting certain resonant times or periods are more stable, more impactful, or possess greater informational coherence, perhaps guiding the universe along specific evolutionary pathways. It's like the universe has preferred rhythms for its own unfolding.
This theory is truly attempting to unify everything, even concepts that typically fall outside the realm of physics. And that includes intelligence. The HHHCR proposes a unified view of intelligence that goes far beyond just biological brains.
This is one of the most sweeping and, for many, perhaps the most thought-provoking claims. The theory suggests that intelligence is not merely an emergent property of complex biological brains, which is our traditional understanding.
Right, we think brains create thought.
Instead, it's fundamentally defined as the coherent resonance of informational fields. This posits that intelligence is an intrinsic property of informational coherence in hyperspace, existing at all scales, not just within biological systems. It's an active process of ordered information flow and processing.
So intelligence isn't limited to humans or even animals. It's a universal phenomenon. Like rocks aren't intelligent, but maybe the field itself has intelligence.
The theory posits that intelligence manifests across vast scales, adapting its form to the informational coherence inherent at that level. So the very small scale, you could talk about quantum intelligence, related to the coherent behavior of entangled and superposed quantum particles and how they efficiently process information at the subatomic level.
Okay.
Then there's biological intelligence, manifesting clearly in neural networks, cellular self-organization, and the complex processes of life itself. That's the one we know best. And all the way up to cosmological intelligence, which refers to the large-scale coherence of structures like galaxies, galaxy clusters, and the intricate cosmic web. This cosmic intelligence might maintain universal stability and facilitate the ongoing organization of matter and energy across the universe.
So the universe itself is, in a way, intelligent, or at least exhibits intelligent organization.
That's the implication that the coherence is a form of intelligence. And it even has a poetic term for this broad spectrum, rainbow intelligence.
Rainbow intelligence, I like that.
Yes, it's a beautiful metaphor used to describe the diverse, multidimensional nature of intelligence as it manifests across different spectra of existence. It suggests encompassing cognitive, emotional, and even maybe spiritual aspects, suggesting that these are all expressions of different forms and scales of coherent information processing.
And if intelligence is fundamentally about coherent information flow, then this theory must also suggest pathways to enhance it, both for individuals and for artificial systems.
It does. Logically, the theory proposes that enhancement methodologies could focus on optimizing this coherent information flow. For biological systems, this might involve neural coherence enhancement, practices like neurofeedback, certain types of meditation, or cognitive training techniques that aim to synchronize brainwave patterns and improve focus and clarity.
Okay, and for AI?
For artificial systems, the focus would be on leveraging quantum coherence in artificial intelligence. By designing AI architectures that maintain and utilize stable quantum states for computation. This could lead to incredibly faster processing, more complex pattern recognition, and more efficient learning algorithms. It suggests a future where AI isn't just about silicon, but about engineering coherent quantum fields, maybe even using hypercrystal-like structures.
Building on that idea of intelligence being fundamental, the theory also re-examines the anthropic principle. The idea that our universe is seemingly tuned for life.
Yes, the fine-tuning problem.
It's a profound philosophical puzzle. Why are the fundamental physical constants and laws of our universe so incredibly precise, seemingly fine-tuned, to allow for the emergence of life and conscious observers? Change them slightly and we wouldn't be here.
This is indeed a classic and persistent puzzle in cosmology. The HHHCR proposes that this apparent fine-tuning is not accidental, but directly linked to coherent resonance in hyperspace.
How so?
The theory suggests that the universe's informational fields are structured in a way that optimizes the conditions for intelligence to emerge and thrive. It's as if the universe has an inherent bias towards organization that facilitates consciousness, and the constants settle into values that support this.
So our universe isn't just accidentally right for us, it's, in a sense, predisposed towards producing intelligence. And this connects quite naturally to the multiverse hypothesis.
Yes, it fits well. In this context, our universe might be just one of many in a multiverse, and intelligent observers will naturally find themselves in universes where the constants allow for their existence. That's the standard anthropic argument.
But how does HHHCR extend this?
The HHHCR framework extends this by describing how different forms of intelligence might arise in different regions of the multiverse, each based on specific coherent resonance conditions unique to that region. It's not just about a universe being right for life, but about a multiverse that explores every possible coherent configuration, and we simply exist in one that supports our particular form of resonant consciousness.
And what are some of these anthropic constraints on physical systems that the theory points to? Give us some specific examples of how our universe just had to be a certain way for us to exist.
The theory highlights several critical constraints that must be within incredibly narrow ranges for life as we know it. For example, the precise value of the fine structure constant, alpha.
Which governs electromagnetism.
Right. It governs how strong the electromagnetic force is. If it were even slightly different, atoms wouldn't form stably, or stars wouldn't be able to fuse elements the way they do, preventing complex chemistry. The very building blocks of life. No carbon, no us.
Okay, what else?
Then there's proton stability. Protons must remain stable for billions of years. If they decayed too quickly, there would be no long-term existence of atoms and molecules, thus no stars, no planets, no life. Everything would just dissolve.
That seems pretty fundamental.
It is. Another critical factor is dark matter density. The universe requires a very specific amount of dark matter for galaxies to form properly. Too little, and galaxies wouldn't coalesce due to gravity. Too much, and they'd be too dense, leading to rapid black hole formation and unstable environments.
So a Goldilocks amount of dark matter.
Pretty much. And perhaps most fundamentally, the dimensionality of space. Our existence depends crucially on having 3 spatial dimensions.
Why 3?
Well, in fewer dimensions, complex structures couldn't easily exist. Think about wiring a 2D brain connections would always have to cross. In a 2D universe, gravity also follows a different law, preventing stable planetary orbits.
And more dimensions.
In more than 3 spatial dimensions, gravity would weaken much faster with distance, again making stable orbits around stars likely impossible. Atoms themselves might become unstable, as electrons could spiral into the nucleus more easily under different force laws. 3 seems to be just right for stable structures and orbits.
So the HHHCR argues that these precise values aren't random, but are emergent from the universe's inherent drive towards informational coherence.
That's the core idea. It's saying there's a cosmic tendency towards coherence and complexity, guiding its evolution in ways that give rise to intelligent life. And our existence is perhaps evidence of that, rather than just a lucky accident. That's a profound shift in perspective.
These are truly profound theoretical concepts. But the HHHCR doesn't stop there. It boldly delves into potential practical applications, attempting to ground these abstract ideas in real-world possibilities.
Right. It tries to bridge the gap from mind-bending theory to tangible innovation, not just philosophy.
Let's explore those applications. Starting with advanced materials. How could hypercrystals lead to capabilities far beyond what we have today?
Well, hypercrystals could inspire the design of incredibly sophisticated metamaterials. Remember, these are engineered materials whose properties come from their structured architecture, not just their chemical composition.
Like tiny antennas or resonators built into the material.
Exactly. By imparting hypercrystalline symmetry, or perhaps quasicrystalline symmetry, which we can make to these structures, we could manipulate waves in entirely novel ways. For instance, we could develop negative refractive index materials, or NRUMs.
Materials that bend light backward.
Essentially, yes. They can bend light backward or exhibit negative phase velocity. This could lead to technologies like perfect lensing, allowing for imaging resolution far beyond what's normally possible due to diffraction limits, or maybe even invisibility cloaking by guiding light smoothly around an object, making it appear to vanish.
The stuff of science fiction.
Getting closer. Similarly, acoustic metamaterials could precisely control sound waves for advanced noise reduction. Imagine silent rooms or targeted sound beams, or cloaking objects from sonar. The unique, multidimensional lattice structures of hypercrystals could, in theory, be engineered to finely tune the propagation of any wave, be it light, sound, or even quantum waves.
We mentioned quasicrystals earlier, and how they're already being used. Are there further applications stemming from this hypercrystal research, particularly in medical innovation, building on what we already know?
Absolutely. Quasicrystalline coatings, which are kind of a 3D shadow of these higher dimensional ideas, are proving exceptionally valuable. In aerospace, their unique combination of high strength, Low friction and wear resistance makes them ideal for critical components in jet engines or spacecraft, significantly extending their lifespan and improving performance under extreme conditions.
And for medical implants, you mentioned joint replacements.
Right. Quasicrystalline coatings provide superior biocompatibility, ensuring the body accepts them, and exceptional corrosion resistance, vital for long-term use within the human body. Critically, their remarkably low friction dramatically reduces wear debris, which is a common cause of implant failure and inflammation over time.
And you mentioned specific manufacturing techniques.
Yes, the paper specifically details advanced optimization methods. For instance, surface treatments like chemical etching or sandblasting are used to meticulously create specific micro and nanoscale roughness on the coating. This isn't just cosmetic, it significantly improves biocompatibility by creating ideal surfaces for cell adhesion and promoting that crucial osseointegration, the direct growth of living bone onto the implant surface, leading to stronger, more stable, and longer-lasting replacements.
And the smooth parts.
For those, cutting-edge additive manufacturing techniques like direct metal laser sintering or DMLS are key. DMLS uses a high-powered laser to melt and fuse metallic powders layer by layer, building incredibly complex, intricate, and precise structures. This allows for the creation of coatings with perfectly smooth, defect-free surfaces where needed, which is paramount for minimizing wear, reducing friction, and ultimately enhancing patient outcomes and implant longevity. It's a prime example of how theoretical insights are leading to tangible, life-changing innovations.
This sounds like a true game changer for material science. Moving on to quantum computing, you mentioned decoherence, the rapid loss of quantum coherence, as the main villain. Does the HHHCR offer a potential solution to this fundamental problem?
It absolutely does, and this is one of its most exciting propositions. The fragility of qubits to environmental noise is quantum computing's Achilles heel. The HHHCR suggests that hypercrystals offer a unique solution by providing inherently stable, coherent regions.
Because they exist partly in higher dimensions.
That's the core idea. Their multidimensional structures could act as robust, fault-tolerant quantum information processing units because the quantum information is intrinsically protected by the hypercrystal's coherent, higher dimensional lattice. The noise just doesn't reach it as effectively.
So specific applications would include what? How would you use them?
This could lead to several breakthroughs. First, we could potentially model qubits themselves as stable, coherent states within a hypercrystal, leveraging its inherent stability to dramatically extend qubit lifetime.
Okay, longer-lasting qubits. What else?
Even more exciting is the possibility of topological quantum computing. In this paradigm, quantum information is stored not in individual particles, but in the global topological properties of a system like knots in the structure.
Harder to unravel.
Exactly. The theory suggests that defect-specific structural irregularities within a hypercrystal might carry a topological charge, making any quantum state stored there inherently robust against local perturbations and environmental noise. A small bump won't change the overall topology. This would be a monumental leap in error correction, allowing for much more stable and scalable quantum computers.
And memory.
Yes. Additionally, hypercrystals could serve as quantum memory devices, storing vast amounts of quantum information in these stable, coherent quantum states for extended periods, far beyond what's currently achievable. This could pave the way for large-scale quantum networks and communication.
Beyond the lab, how does this theory give us new cosmic insights, redefining the universe at its largest scales? Does it connect to quantum gravity or string theory, which also posit extra dimensions?
It certainly offers intriguing connections. In the realm of quantum gravity and string theory, which attempt to unify all forces, extra dimensions are often theorized to be compactified or curled up at incredibly small scales, so we don't see them directly.
Right, the hidden dimensions.
The HHHCR suggests that hypercrystals might represent stable configurations of fields or perhaps strings in these higher dimensions. It could provide a geometric framework that contributes to our understanding of how these extra dimensions manifest or are stabilized. Maybe they're not just curled up randomly, but form these coherent structures. It offers a new, potentially observable perspective on these fundamental concepts.
And what about black holes? They're already mysterious enough in 3D. Does the theory give us new insights there? They're often linked to fundamental physics.
Intriguingly, yes. The theory proposes that black holes could have fractal event horizons.
Fractal horizons, not smooth spheres.
Exactly. Instead of being smooth, perfectly spherical surfaces, they might exhibit incredibly intricate fractal patterns across multiple scales. This concept could have profound implications.
Like what?
For instance, it might influence phenomena like Hawking radiation. Instead of emitting a continuous thermal spectrum, a fractal horizon might lead to a discrete set of energy levels for Hawking radiation that depend directly on the fractal dimension of the horizon.
A signature we could potentially look for.
Potentially. It also suggests that the waveforms of gravitational waves emitted by black hole mergers might be influenced by this fractal geometry. The precise shape of the chirp signal could depend on the fractal dimension of the surrounding spacetime. This offers another potential pathway for observational validation, though extremely challenging.
So we're talking about direct observational signatures of these hidden dimensions, possibly encoded in black holes or gravitational waves. What about the biggest cosmic mysteries? Dark matter and dark energy. They make up most of our universe but remain largely elusive.
The HHCR-TOE offers compelling new perspectives on these enigmas, too. Dark matter, for instance, which provides the gravitational scaffolding for galaxies but doesn't interact with light.
The invisible stuff.
Right. It could be composed of stable hypercrystalline structures that exist primarily in higher dimensions and therefore interact only very weakly with ordinary matter in our 3D space. This would naturally explain their invisibility and why they are so difficult to detect directly while still having mass and gravitational effects.
And dark energy, the force accelerating the universe's expansion.
Dark energy might be understood not as some exotic substance, but as negative pressure arising from coherent resonance patterns at the cosmic scale. This pressure would be a direct reflection of the influence of these vast hypersymmetric structures on the fabric of space-time itself, essentially pushing space apart as a consequence of the resonance state. It's not an arbitrary force, but a manifestation of fundamental hyperdimensional dynamics.
And it even provides a new angle on the famous horizon problem, which is the puzzle of the uniform temperature of the cosmic microwave background. Traditionally, cosmic inflation solves this by saying distant parts of the universe were once close enough to thermalize before being rapidly expanded.
Exactly. The horizon problem asks, how can regions of the cosmic microwave background on opposite sides of the sky be at the same temperature if they were never in causal contact in the early universe, according to standard cosmology without inflation? They shouldn't have had time to talk to each other.
Right. Inflation stretches a small, uniform patch.
While cosmic inflation is the leading solution, hyperspace coherence might offer an alternative or perhaps complementary solution. It suggests that fundamental information and coherent resonant patterns can propagate across the entire universe through these higher dimensional connections, maintaining uniform properties even over vast distances that would otherwise be causally disconnected.
So the universe is uniform because it's all connected at a deeper, higher dimensional level.
That's the idea. This inherent coherence stemming from the underlying hyperspace could mean the universe's structure simply remains uniform due to these deeper, higher dimensional resonances, potentially reducing the sole reliance on a period of rapid inflation, or perhaps working alongside it.
This is all very theoretical. But the paper also discusses how we might begin to make it real, detailing fabrication and simulation techniques. How do scientists bridge theory to reality for something so abstract, existing in higher dimensions? It seems impossible to build something in 4D.
It's a huge challenge, absolutely. We can't directly build in 4D, but scientists are already working on fabricating materials inspired by these ideas, materials with hypercrystalline or, more practically, quasicrystalline properties, using incredibly high-precision methods.
Like what kind of methods?
These include top-down techniques like electron beam lithography, or EBL. Here, a finely focused electron beam is used to etch or draw incredibly precise nanostructures onto a material surface, often with resolutions down to just a few nanometers. Think of it like nanoscale carving. Similarly, focused ion beam, or FIB, milling uses a focused beam of ions to precisely remove material.
Building down. What about building up?
Yes, there are also bottom-up methods, like the spontaneous self-assembly of nanoparticles, where tiny building blocks spontaneously arrange themselves into complex patterns under the right conditions, or techniques like molecular beam epitaxy or vapor deposition, where materials are deposited atom by atom or molecule by molecule to form thin films with specific crystalline or quasicrystalline structures.
And what about cutting-edge approaches like 3D printing? Are those involved? Seems like they could make complex structures.
Absolutely. Emerging techniques within additive manufacturing, often known as 3D printing, are crucial here for building complex, custom structures layer by layer, especially those inspired by these complex symmetries. This includes things like selective laser melting, SLM, and direct metal laser sintering, DMLS, which use powerful lasers to fuse powdered materials like metals or polymers into intricate 3D shapes based on a digital model.
And for really fine details.
There's also two-photon polymerization, a highly precise 3D printing method that uses focused laser light to solidify light-sensitive resins at tiny focal points, enabling the creation of structures with incredibly fine features, often on the micro and nano scale.
So you could print, say, a metamaterial designed with quasi-crystal principles.
Exactly. For applications like photonic crystals, which control light flow, there's a strong focus on optimizing resolution, selecting materials for ideal refractive index contrast, and implementing defect engineering, deliberately introducing specific structural flaws to create desired optical properties, like guiding light along a specific path or creating forbidden band gaps for certain light waves. These techniques are vital for translating theoretical designs, even those inspired by higher dimensions, into physical reality we can test.
Since direct observation of these multidimensional hypercrystals is understandably quite difficult, simulation and modeling must be crucial. How do they visualize the unseen and test these abstract concepts computationally?
Computational power is absolutely essential for exploring the implications of this theory. You can't do it otherwise. Sophisticated numerical methods are used extensively.
Such as?
Things like finite element analysis, or FEA, which breaks down complex geometries into smaller, manageable elements to simulate things like wave propagation, stress distribution, or heat transfer in complex materials, even those with theoretical hyperproperties. Monte Carlo simulations are also vital for modeling quantum systems in quasicrystals or hypothetical hypercrystals, allowing scientists to predict their behavior over time through probabilistic calculations.
Does the paper give specific examples of these simulations?
Yes, it provides a concrete example detailing how to solve the Euler-Lagrange equation, a fundamental equation in physics for finding stable states for hypercrystal formation, specifically in a 4D hyperspace, using finite difference methods and periodic boundary conditions.
So they actually simulate a 4D crystal forming?
Computationally, yes. This involves discretizing the 4D hyperspace into a grid and then computationally finding the stable resonant patterns, the solutions to the equations. While we can't see 4D, the visualization of a 2D slice taken from this computed 4D grid, showing the distribution of the resonance function, CI, provides a concrete example of how these abstract concepts are explored.
Like taking a cross-section.
Exactly. It allows researchers to visualize the stable nodes and patterns that would constitute a hypercrystal in a higher dimension, essentially providing a snapshot of these otherwise invisible structures and allowing them to check if the mathematical framework produces stable, ordered results consistent with the theory.
This brings us to the deepest dive, the philosophical and future implications of the HHHCR-TOE. It's truly proposing a new kind of theory of everything. How is it different from previous attempts?
Indeed. What's revolutionary here, I think, is how it redefines what a theory of everything actually means. Traditionally, it's been about unifying the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, maybe explaining particle masses.
The standard model plus gravity.
Right. But the HHHCR-TOE radically redefines everything to include how reality is fundamentally organized, processed, and transmitted as information. It's not just about particles and forces, but about the underlying informational architecture from which they emerge.
So it's not just a physical unification, but a metaphysical one, incorporating information as fundamental.
Precisely. This framework consciously challenges the traditional boundaries between science and metaphysics, proposing a unified understanding that encompasses not just the material realm, but informational and even conscious realms. It suggests the universe is a vast, self-organizing information system where physical reality, including forces, particles, and space-time, emerges from the coherent organization and resonant patterns of information within a higher dimensional hyperspace. It's a grand synthesis attempting to connect physics to information theory at its deepest level.
And this leads us to a truly revolutionary potential application.
Yeah.
Energy from hyperspace, specifically zero-point energy extraction. This sounds like free energy.
Well, free is always tricky, but the theory does reconceptualize energy itself in a way that might make ZPE accessible. It suggests a profound redefinition. Energy is not just a separate, distinct entity, but the tangible manifestation of coherent resonance in hyperdimensional space.
So energy is resonance.
In this view, yes. When informational patterns align and resonate perfectly within these higher dimensions, they manifest as observable energy in our 3D reality. It challenges the classical notion of energy as a static quantity and instead positions it as a dynamic process of resonant alignment and amplification within the hyperspace fabric.
And this ties into zero-point energy, which is that lowest possible energy existing even in a vacuum due to quantum fluctuations. It's there, theoretically immense, but famously inaccessible.
Yes. Zero-point energy, or EPE, represents the fundamental quantum fluctuations of the vacuum, a sea of virtual particles constantly popping in and out of existence. While potentially immense, it's generally considered non-extractable because it's uniform everywhere. However, the HHH-CRTO proposes that ZPE is not just a static background noise, it's actively modulated by the coherent resonance of hyperdimensional structures, potentially making it far more accessible for extraction. This is a crucial leap. It's not about inventing energy out of nothing, but about accessing and manipulating what's already there in the vacuum in a profound new way by resonating with its deeper, higher dimensional origins and potentially creating gradients or structures within it.
So it's like a higher dimensional Casimir effect, but on a grand scale, where the Casimir effect shows forces from vacuum fluctuations between plates.
Exactly. The well-known Casimir effect is a small attractive force between two uncharged parallel conductive plates in a vacuum, arising from the modulation of vacuum fluctuations between them. Certain wavelengths are excluded. By extending this effect to higher dimensional surfaces or structures, the theory suggests that by manipulating the geometry of these higher dimensional resonant structures, or objects engineered to resonate with them, we could profoundly alter the vacuum energy density on a much grander scale, leading to significantly enhanced ZPE extraction.
Tapping the vacuum.
The idea is that manipulating hyperdimensional geometry influences the distribution and intensity of quantum fluctuations in ways that could be harnessed for energy, perhaps creating localized imbalances we could draw from.
And what are the practical pathways envisioned to achieve this? From a materials and engineering perspective, this sounds incredibly difficult.
Extremely difficult, yes. Purely theoretical at this stage. But the theory envisions the development of hyperdimensional resonators. These would need to be designed with incredibly advanced materials.
Like what?
Things like superconductors, which allow for lossless current flow and strong magnetic fields, metamaterials engineered for specific wave manipulation, as we discussed, graphene with its unique electronic properties and 2D structure, and perhaps quantum dots for precise quantum control. These materials would form the basis of devices capable of dynamic resonance tuning.
Meaning they could be tuned like a radio.
Essentially, yes. They could be precisely adjusted to resonate with specific coherent patterns predicted to exist in hyperspace. If successful, such innovations would pave the way for revolutionary energy technologies, potentially providing a clean, abundant, sustainable energy source. It truly is a potential game changer for humanity's energy future, albeit a very distant one.
This is truly astonishing, bordering on science fiction, but grounded in a theoretical framework. And perhaps the most provocative implication is about consciousness and spirituality. Does the HHH-CRTO suggest a scientific basis for these, beyond our current understanding?
It certainly goes there, and very boldly. The theory suggests that consciousness is not necessarily an accidental byproduct of complex biological brains, emerging only from sufficient neural complexity.
Which is the standard view.
Instead, it's posited as an emergent phenomenon, arising from the coherent resonance of hypersymmetric information patterns. It views biological systems, including the human brain, as highly intricate hyperdimensional resonant structures themselves, capable of tuning into and processing these higher dimensional informational fields. The brain as an antenna, almost.
This sounds very much like panpsychism, the philosophical idea that consciousness, or at least a proto-consciousness, is fundamentally embedded in all matter, not just brains.
That's a direct alignment, yes. The HHH-CR framework suggests that individual consciousnesses are localized resonant structures within a larger, perhaps universal conscious system or field. Our individual awareness is a specific manifestation, a localized coherence of this broader field of coherent information.
And the really provocative part, spiritual experiences.
But perhaps most provocatively, the theory proposes that spiritual experiences, things like profound meditative states, experiences of unity, out-of-body experiences, or sudden spiritual awakenings, could potentially be understood as direct, resonant interactions with higher dimensional structures.
So it's not just subjective or mystical. It could be a real, quantifiable interaction with a deeper layer of reality described by the theory.
That's the implication. It offers a novel potential scientific basis, or at least a scientific language for phenomena, described across many mystical and spiritual traditions that often describe reality as a multi-layered, interconnected system, speaking of higher realms or planes of existence.
How would that work?
The theory suggests that by altering our own state of consciousness, perhaps through practices that enhance neural coherence, individuals could potentially align with or tune into the resonant frequencies of these hyperdimensional structures. This could allow access to higher states of awareness, profound insights not accessible through ordinary analytical thought, or even experiences of unity with the larger cosmic intelligence. It provides a potential scientific framework for phenomena previously confined entirely to the spiritual or psychological realm.
#backtag outro.
What an incredible journey we've taken today. Seriously. From the familiar world of 3D crystals to the mind-expanding realm of hypercrystals and the incredibly ambitious HHHCR2. It's a lot to take in. It really is. We've seen how this theory attempts to redefine everything from the fundamental nature of space and time to the very essence of information, and even our understanding of intelligence and energy, all through these underlying mechanisms of hypersymmetry and coherent resonance across hidden dimensions.
This deep dive has truly challenged conventional wisdom, I think. It opens up startling new possibilities for understanding the universe. It suggests that physics might be far more interconnected and information-driven than we currently imagine, with unseen dimensions playing an active, shaping role in the reality we experience every day.
Yeah.
It paints a picture of a cosmos that is inherently ordered, potentially intelligent in a broader sense, and brimming with potential we haven't even begun to tap into.
Indeed. So here's a final thought for you, our listener. If the very fabric of our universe is woven with these intricate hyperfractal patterns, and the stability of reality truly depends on the coherent resonance of information across hidden dimensions, what does this imply for our own place within this magnificent cosmic network?
And how might we, as intelligent beings, perhaps as localized resonant structures ourselves, learn to better understand and even tune into the universe's deepest symmetries to unlock new insights and possibilities for the future?